Okay, so still on anaerobic adaptions, the anaerobic energy system. So during high intensity and short duration exercises, we use anaerobic systems to provide energy to resynthesize ATP. These are the PC, which is phosphocreatine, and the glycolysis system, both anaerobic. Here's my mouse, there it is. Here is a typical Wingate test graph. The green line represents the untrained individual, and the black line represents after the training program. After the training, the system and its anaerobic enzymes become more efficient at breaking down glucose as a fuel source, as shown on the graph. Also shown on the graph, there are three main points of adaptation. Firstly, there is a higher peak point here, higher than the green line, meaning that the system can produce more power after training. Second, the person reaches their peak power point a lot faster after training, showing that the system is now faster than before and more efficient at quickly making ATP. Lastly, the person after training finishes with more power and a lot higher on the graph. This is due to the increased resistance to the buildup of lactic acid. A trained individual is able to delay OVLA, preventing the buildup of lactic acid and therefore fatiguing less, so they're able to sustain this power level more. So in terms of lactic acid, here we have some results for blood lactate of an untrained individual during the Wingate test. At the end of their test, their lactate level was 9.1 moles. After an 8-week training program in the same exercise, we would expect a decrease in this value to about 5 millimeters moles. This is because the pH buffering system has more efficiency to prevent buildup of lactic acid, and therefore they're able to delay this. For a 400-meter runner, which is an aerobic exercise, being able to delay OVLA is crucial, as it helps to prevent fatigue in their working muscles and therefore allowing them to keep their power level relatively constant throughout the whole race. So they would train anaerobically in order to gain these adaptions. Onto the adaptions in the skeletal system. Anaerobic exercise can put stress on the skeletal structure and therefore can cause adaptions to happen in the bone structure. During this type of exercise, there is a large amount of friction and pressure on the joints. The cartilage in the joints prevents the two bones from rubbing on each other. Here, you see we've got articular cartilage. After this 8-week training program, an athlete's cartilage will become much thicker and able to deal with the contact in this type of exercise. So for a 100-meter sprinter, thicker cartilage is crucial as it helps to prevent injury, so they can still train and race continually without any major injuries to the joints. So for example, cartilage in an untrained person is normally about 2 to 3 millimeters thick. After training, we would be able to estimate that this would increase to about 4 to 6 millimeters, depending on the training program and how much they put stress on their joints. The joints also become used to moving in all sorts of planes depending on the activity. So we have a picture of a sprinter who is in a very, very athletic pose and in lots of different planes and range of movement. So here we can see that the joints become more used to these planes and acting in these large overstretched positions, so therefore this increases the joint's overall range of movement after long periods of training. As mentioned before, tendon strength as well as ligament strength also increases, which provides further stability for the joint and also helps to prevent further injury. Okay, so now we're on to the aerobic adaptions of the body. Aerobic exercise is a low intensity and short duration activity. This means that the body is working with oxygen to keep the body going. So therefore, the adaptions of this system will be specific to the use of oxygen. These adaptions will increase a performer's VO2 max, which is the maximum amount of oxygen which can be consumed, also known as their aerobic capacity. Increasing their VO2 max will increase the amount of oxygen the athlete's body can use and therefore increase their effectiveness of working aerobically. These adaptations can be brought about through long-term training, 6 to 8 weeks working aerobically, as we mentioned in the first video in the intro. So, the first system is the respiratory system. Similarly to the anaerobic adaptations, hypertrophy of the respiratory muscles takes place, increasing their strength and power, so these muscles get stronger. This allows the lungs to breathe deeper and therefore increases the tidal volume, meaning more oxygen can be breathed in per breath. This happens as the conditions of the training program has put pressure on the lungs to adapt. This increases tidal volume, which decreases an athlete's breathing rate during an exercise as they need less breaths for the same amount of oxygen, very similar to the anaerobic adaptations. So for example, we carried out a 20-minute continuous steady state exercise on a gym bike for an untrained individual at low intensity with relatively long duration. At rest, the untrained individual's breathing rate was 13 breaths per minute. After training, after an 8-week training program, we would estimate a decrease in this to about 10 breaths per minute. At the end of the test, their breathing rate was 26 breaths per minute, and after the training program, we could estimate that this would decrease to about 22 breaths per minute, as the adaptations of the muscles and the respiratory system has increased the tidal volume, which therefore decreases the breathing rate. So the alveoli in the lungs also increase in size due to the aerobic training program. Larger alveoli increases the surface area for diffusion of oxygen into the bloodstream. This means gas exchange is more effective during exercise, so more oxygen can get into the body and therefore VO2 max increases. These adaptations combined can help increase an athlete's performance. For example, a marathon runner will be more effective at getting oxygen into their body, therefore allowing them to work aerobically for longer, as well as decreasing the effects of fatigue in the form of oxygen deficit. This can help them finish the race with a faster time and beat opponents. So, moving on to the cardiovascular system. Hypertrophy of the myocardium walls takes place after an 8-week aerobic training program, shown in this diagram. This increases their strength when contracting, which means the heart can pump more blood out per beat. This is their stroke volume. More blood per beat means that the heart rate will decrease, as less beats are needed to pump the same amount of blood. So for example, in the 20-minute test, an untrained individual's heart rate was 82 beats per minute at rest. After the training program and these adaptations have taken place, we would expect a decrease to maybe about 62 beats per minute. The post-test value was 108 beats per minute, and similarly, we would expect to see a decrease after the training program to about 95 beats per minute. As well as these adaptations, capillarization happens around the muscles and lungs. This helps increase the efficiency of gas exchange, meaning more oxygen can diffuse into the muscles and oxygen can diffuse in through the lungs into the bloodstream. This means the athlete is able to work aerobically for longer. This is capillarization here. Blood pressure is also decreased as an adaptation due to the blood vessels become used to stretching under pressure, as we mentioned before in the previous video, similar. An athlete who trains aerobically for 8 weeks has also less chance of getting diseases such as heart disease and coronary heart disease. Moving on. So the neuromuscular system. After an aerobic training program, slow oxidative fibers experience hypertrophy, becoming stronger and denser, not necessarily bigger, but denser. This makes the contractions more consistent and more effective at working with oxygen. They are therefore well suited to aerobic exercise and helps a performer, like a marathon runner, be better suited to their activity. As well as this, more mitochondria are produced in the muscles as a result of training. Mitochondria here is the site of aerobic respiration. So more mitochondria means that the performer is able to work aerobically for longer because more mitochondria are carrying out aerobic respiration, so there's more ATP being produced. Myoglobin here, myoglobin stores myoglobin stores oxygen. Myoglobin stores also increase after this training program, meaning the muscles can store more oxygen, which increases VO2 max, so they can consume more oxygen. In a regular untrained person, 90 mcg/L myoglobin is a regular person's myoglobin store. That's how much they have. After a long-term training program, training aerobically, we would expect this to increase to 120 mcg/L as myoglobin becomes more oxidative and their stores increase. All these adaptions are well suited to a marathon runner, as mentioned, and would help them improve their performance by increasing the amount of oxygen available to their working muscles, their VO2 max, increasing their VO2 max. So lastly then, we have the adaptions of the aerobic energy system. When working at low intensities and long durations, we are using the aerobic system to provide ATP for energy. There are a few adaptions from training that make this system run better. One is an increase in aerobic enzymes and the effectiveness of them. These help in the aerobic process and breaking down of materials in the Krebs cycle. So more aerobic enzymes speeds up the respiration process, making energy available quicker. Another is the body's ability to reserve glycogen stores and burn fat as an alternative fuel source, which is also shown to provide more energy. Normative RER values in this table here for an untrained person is 0.84, and as shown in the graph, 0.84 is 53% fat and 47% carbs used. After training, we would expect to see the RER value drop to about 0.80, which is 68% fat used and 32% carbs used, showing that after training, the body gets used to using more fat and saving the carbs to help reserve them. So these two combined make the system more effective, and therefore the athlete can use it for longer rather than using the anaerobic glycolysis system, which builds up lactic acid and causes fatigue. So by increasing the effectiveness of the aerobic system, the athlete is able to delay OBLA and therefore delay fatigue. For example, in our 20-minute test, the blood lactate score for an untrained person at the end of the steady state test was 20.9 millimeters moles. After training aerobically for 8 weeks, we would expect to see this decrease to about 10 millimeter moles, which is, so the results shown in the graph. These adaptions are important to keep an aerobic athlete at top performance. For example, it's important for a marathon runner to use more fat stores, so therefore glycogen stores don't get depleted, as we mentioned, so they don't hit the wall, which is caused by lack of glycogen stores, and they collapse, basically preventing them from finishing the race, which is not what they want at all. So as well as this, aerobic training is important because aerobic athletes want to work, marathon runners want to work with oxygen for as long as possible, so they can avoid fatigue and lactic acid buildup, so they can keep working aerobically without fatigue.